Hey everyone, it is Chemistry 1112 with the one and only Dr. Carroll. We are into the last chapter of the course. Now, it is chapter 17, Electron Transfer Reactions, all about the redox and the electrochemistry. We don't need to see that anymore. Redox and electrochemistry. Redox, oxidation, reduction reactions. Electrochemistry, we're talking about creating electrical currents in galvanic cells, also known as voltaic cells, and using electric currents to make things happen in electrolytic cells. If you need a brief refresher in all this, go to this website, tinyurl.com/chem U7S1. That's actually a YouTube link to my grade 12 introduction to oxidation reduction and electrochem. Watch it at 2 times so I'll sound like Alvin and the Chipmunks. And for extra fun, put on the closed captions. It is fun to do. Okay, I will pause and see you in 34 minutes. And we're back. Okay, so let's go. I love doing that. Let's go to the pictures here on page 828. We have a rusty bridge and we have some rusty machinery there. And so we're going to quickly go over some of this since you just saw a nice review. Recognizing redox reactions, balancing redox reactions. Oh yeah, we're going to balance in the lovely 7-step method. We're going to balance in acidic environment, basic environment, neutral environment. We're going to look at galvanic cells, which are going to spontaneously pump electrons around, right? Dry cell primary batteries are examples of galvanic cells. Cell potentials, how much force is used to push those electrons around a current. Free energy, how that's related to electrochemistry. Examples of redox in action, like we'll look at some corrosion processes, and electrolysis, which is electrolytic cells, and it's going to be fun. Okay, there's some corrosion at the beginning. So, page 829, redox, one species lose while another gains. Remember, oxidation is the loss of electrons, reduction is the gain. So we have oil rig, oxidation is loss, reduction is gain. Another one I saw is Leo the German. So Leo is loss of electrons, German is a gain of electrons. I've seen Leo the lion says great. No. Leo the lion says grr. That's right. Tony the tiger says great. Okay. Enough of that silliness. So the reactant that is transferring electrons to the other reactant is called the reducing agent because it's causing the other electron to be reduced. The other reactant to be reduced. The reactant that is causing the other reactant to lose electron is called the oxidizing agent because it's causing the other electron to be oxidized. So we can summarize that. I'm going to put this up here. Reducing agents. I don't like the thickness of that one. Let's make it thinner. Reducing agents themselves are oxidized. They technically contain the element or elements that are oxidized, and oxidizing agents are reduced, technically contain the species that has at least one thing in it reduced. Not all chemical reactions are oxidation reduction reactions, but if there are oxidation reduction reactions, one thing at least has to be oxidized while one thing at least has to be reduced. So, transfer electrons. It's possible for oxidation to occur without reduction. Here's a redox reaction involving magnesium to form magnesium oxide. So magnesium has an oxidation number of 0. You saw that in the review. Oxygen also has an oxidation number of 0. And the product, magnesium, is +2 and oxygen is -2. So we have magnesium going from 0 to +2. So the oxidation number goes up. So that means magnesium is undergoing an oxidation. Oxygen goes from 0 to -2. So the oxidation number goes down. So oxygen is undergoing a reduction. So the oxidation means you are losing electrons. Your electrons are liberated. So there's magnesium goes to magnesium 2 plus 2 electrons. And then the O2 gobbles up electrons to have it all nicely balanced. 4 electrons to form 2 O2 minus. You add those two together. We have to multiply this by 2, as we'll see. Anyways, you have oxidation half reaction here, reduction half reaction here. Okay, then I already talked about reducing agent, oxidizing agent. Oxidizing agent is also called an oxidant. You sometimes hear that phrase. So a creature that causes something else to be oxidized is an oxidant. You should really not store oxidants and reducing agents in the same cupboard in your chemical storeroom, because that is asking for trouble, because that's how reactions can happen. Okay, and you want those to happen under controlled systems. In an experiment, you don't just want to store them, reducing agents and oxidizing agents beside each other. Oxidation numbers. The book goes into way more detail than you have to. You know the rules from Chem wu17lec1, the YouTube video you just watched at 2 times. You don't have to watch it at 2 times. You can watch it at 1 time if you want. Treat polyatomic ions separately. There are some things that are a bit more advanced than what we did in grade 12. For example, if you have sodium nitrate and I want to get the oxidation numbers of all those things, okay, I mean the hydrogen's +1, oxygen's -2, but then you're saying, what the devil do I do with the nitrogens? So think of that as being an NH4 plus and an NO3 minus. And then oxidation of oxygen is almost always -2. With peroxides, it's -1. I think we'll see some examples of that. And then the nitrogen would be +5. Because you have 5 plus -6 gives me -1. And hydrogen with nonmetals is +1. And so the nitrogen here has to be -3. So that gives you +1 for the ammonium and -1 for the nitrate, and it all works well. And so you see that the nitrogen associated with the ammonium has an oxidation number, this fictitious bookkeeping system number of -3, and the nitrogen of 5. Sum of all oxidation numbers makes it equal to the charge of the species. Okay, that one we've seen before. Hydrogen usually has an oxidation number +1. When wouldn't it? If you have a binary metal hydride, then it isn't, like sodium hydride. Sodium, alkali metal, likes to be +1 for the oxidation number, and that priority is more important than the hydrogen +1 rule. Okay, again, join IUPAC, join the union, you can help make the rules. So sodium's +1, hydrogen's -1. Or calcium hydride, hydrogen is -1 because calcium is +2. The alkaline earth metals want to be +2. But something like phosphine, pH 3, hydrogen is +1, phosphorus is -3. Fourth rule, over and above the rules we've learned in the first high school screencast you saw earlier today. The most electronegative atom is negative oxidation number. Forget about that octet business, but just if I have something like chlorine monofluoride, ClF, you say, oh, what do we do here? 2 halogens. Well, fluorine's more electronegative, so it gets the -1, and chlorine gets the +1. Or fluorine likes to be -1 lots of times. There's no specific rules for aluminum, but fluorine likes to be -1, so it's -1, and the aluminum is +3. Think of it as an ionic compound. That's a good way to think of that. I knew ammonium nitrate was there. I wrote it down and I said, oh, I bet this is supposed to be there. Oxidation number of atom and pure neutral elements is 0, so this is all 0. Monatomic ion has the same as the charge. Okay. Hydrogen is +1, except the hydrides. We talked about that. Nitrogen can have all sorts of values. Oxygen is -2, except in hydrogen peroxide, where it's -1. Instead of rules, they talk about guidelines, right? Because hydrogen would be +1, so oxygen is -1. Sodium peroxide, sodium is +1, so oxygen is -1. Okay. Cn-, what's the story on that one? This is a good one here. How would we handle that? I mean, I know if it's HCN, no, that wouldn't help either. Hydrogen is +1, Cn is minus. Excuse me. Cn-, where we assign oxidation numbers of -3 to nitrogen and +2 to carbon. Okay, so in that case there, this is one we haven't encountered before, but we'll assume, even though there's a covalent bond, to get the oxidation number, you assume it's ionic, and nitrogen is 3 off from forming a completed shell, and so then what's left over is the carbon has to be +2. Okay, so that's a rule we won't see often, but there it is. Okay, assign oxidation numbers to all the atoms in these two reactions involving iron. So the first one for practice, iron has to be +2 because oxygen is -2. Carbon monoxide, oxygen is -2, carbon's +2. Some books don't put the little circle above it, like ours doesn't, but others do. I like to. Iron is 0 on the right hand side. Oxygen is -2 in carbon dioxide, and the carbon's +4. Okay, so just milking this a little bit. So iron oxide is reduced. If the oxidation number goes down, then it's reduced. Okay, so iron oxide is reduced. And so what about the oxygen? Well, to balance it, we'd have to, maybe it is balanced already. Okay, so the oxygen doesn't change, but we do need something to be oxidized, and that's the carbon. It goes from +2 to +4. Okay, FeCO3, so iron's +2 because the carbonate ion is -2, so the oxygen is -2. The carbon has to be +4. 4 and -2 times 3, so 4 plus -6 is -2. Iron's +2. So we've got FeO, oxygen's -2, iron is +2. Then CO2, oxygen is -2, carbon is +4. Okay, so the iron stays the same. The carbon goes from +4, well, stays at +4, and the oxygen stays at -2. So this one here, in fact, it is a chemical process, but it is not an oxidation reduction process because you don't have changes in oxidation numbers. In fact, it is just the decomposition. Oh, no, it's not the decomposition. It is a rearrangement. It's driving out. Actually, it's a gas formation reaction, isn't it? You're driving out carbon dioxide. Okay. Is all this good? FeO -2, iron +2, oxygen -2, carbon +2, iron 0, oxygen -2, carbon 4. Good. Second one. So plus iron is oxidation number 2, carbon's +4, and then they summarize the oxidation numbers. And for some reason they put the oxygens underneath. I think that's because otherwise it would get too crowded. So I talked about the reduction and the gaining. And again, yeah, it's not a redox process. Oops, sorry. Fit to page. No, I don't want that. I want to make it larger. Well, that's as large as it's going to go. That's okay. That's large enough for us, right? Okay, so that's good. Practice exercise. Shall we do that really quick? NiO plus C. So carbon is 0. Oxygen is -2. Nickel's +2. Transition metals can have a variety of oxidation numbers, as we'll see through the chapter. Nickel 0 here, oxygen's -2, carbon's +2. This is going to be a redox process with the nickel reduced from NiO to Ni and the carbon oxidized. There's no such word as oxygenized or oxidization. It's oxidation, not oxidization. Oxidation. You got nickel is 0, oxygen is -2, carbon is +2. Okay, now look at this one here. We got nickel, then we got CO4. Now this is a bit advanced. The CO actually is 0, so the oxygen is -2, the carbon is +2, and the nickel is 0. Now, of course, I'm going to look at practice exercise 17.1. That one is over and above what we would have to do. That's talking about a metal complex thing. But let's take a look at it here. 17.1. CO has not changed, so O is -2, carbon is +2, and Ni is 0. So that one is not a redox process. Okay, I'll let you do. You know what? Let's do it together. Why not? Okay. H3PO4. Oh, okay. That's even better. I'll do this on another piece of paper so it doesn't get all squished in there. This is going to be page 833, example 17.2. Okay, file, new. Okay, so H3PO4, let's write them all out here. H3PO4, then O3, NaOCl, ClF3, KH, and I might as well do the two practice ones, H2SO4 and KClO3. Okay, shall I show off and use a different color? Why not? Is this my color wheel? Okay, oh, let's use that. Nice blue. Okay, so hydrogen is going to be +1, oxygen is -2. Do the ones you know first. So -8 and +3 is -5, so phosphorus has to be +5. O3, well, that's going to be 0 all the way around. NaOCl. So sodium is +1, the hypochlorite ion is -1, oxygen is -2, chlorine's +1. Okay, oxygen likes to be -2. It's more electronegative than chlorine also. Typically the oxidation numbers, if everything else is sort of borderline, you want the more electronegative atom to have a negative oxidation number. ClF3, well, yeah, that's what we just talked about. Fluorine's going to be -1, chlorine +3. KH is one of those binary metal hydrides. So hydrogen is -1, potassium is +1. H2SO4, oxygen is -2, sulfur is +6, hydrogen is +1, so that all works. KClO3, potassium wants to be +1, and the ClO3 is a minus, oxygen is -2, so chlorine is +5. So chlorine can certainly have a wide variety of oxidation numbers. Okay, all looks good to there. Good. Okay, let's jump back to the page here, section exercises, determine the oxidation numbers. Okay, you can do that on your own. 17.1.2, determine which are redox, what's reduced, what's oxidized. I went through that. You can do that yourself and assign oxidation numbers to all the nitrogen atoms in each of those. You can do that yourself. I have 100% confidence in you. Okay. Balancing redox reactions. Okay, you're going to break things down into two halves. The details of this are in that first YouTube that you saw. So, this book likes to use H3O plus instead of H plus for balancing an acidic environment. I'm going to use H plus, and then at the very end, to make it look like the book, I'll just add waters to both sides so they will combine with the H pluses to give me H3O pluses when I'm balancing in acidic environment. When I'm balancing in basic environment, here's a trick. Now, not every book does this, but the cool people do. I'm going to pretend it's an acidic environment, and then at the very end, I'm going to add OH minuses to both sides. Okay, so identifying half reactions. Really, they want me to go through this? They want to hold our hand before we get into the guts of balancing redox. By the way, why do we care about balancing redox? Because it helps us understand and predict what voltages there are in cells. It helps us understand oxidation reduction titrations, which are important in forensic medicine when you're studying blood scenes from a crime scene, and you want to do this kind of analysis to find out what the heck was going on. So we have some examples here of separating things into oxidation reactions in half. I'm going to go straight to examples of balancing. There are times though where you see where one thing goes into two other things. That's called the disproportionation reaction. And just to look at this one for a second here, BrO2 minus. So you might say, well, how can I have this into an oxidation half reaction, which I call an OHR, and a reduction half reaction, when there's only one thing on the left? Well, when we balance it, there's going to be more than one thing on the left. So some of the BrO2 minus are going to be oxidized to form BrO3 minus, and some are going to be reduced to form BrO minus, right? BrO2 minus, oxygens minus 2, bromines plus 3. So that gives a total of minus 1. And here, oxygen minus 2, bromines plus 5. So you're going to have oxidation, like I said, from BrO2 minus to BrO3 minus. Br minus is minus 1, so I'm going to have reduction from BrO2 minus to Br minus. Okay? And so that's good. There's the whole story. Now let's jump right into it, okay? So I'm not even going to look at the way they do it. I'm just going to take this example 17.4 and go to the big whiteboard in the sky. No, not in the sky, on the screen, and solve for this. So example 17.4, which is on page 836. Okay, file, new, maintain ratio, sure. Let's get the image a little bigger, right? View. I think just change the canvas size to 130 is good enough. Okay, so there's my canvas size. So the unbalanced reaction, this is an acidic environment. I'm not going to worry about the phases till the very end. Cr2O7, 2 minus, plus Fe2 plus. This is example 17.4. Goes to form Cr3 plus Fe3 plus. Okay, so this is what we want to solve for. So we got to start by assigning oxidation numbers. So oxygens minus 2, chromines plus 6, ions plus 2, chromines plus 3, Cr3 plus, and Fe3 plus. Okay, now we want to decide what's oxidized and what's reduced. So chromium goes from plus 6 to plus 3. So that is reduction. Ooh, that was cool what I did there, wasn't it? And ion goes from 2 plus, or plus 2 to plus 3, so that's oxidation. Typically, the oxidation numbers are written with the algebraic sign first and then the number, whereas the actual charges are written a number and then an algebraic sign. So I typically write the oxidation half reaction first. Let's get into a bit darker story there. So oxidation half reaction, you just write the bare bones of what's oxidized. So we got Fe2 plus goes to Fe3 plus. And reduction half reaction, you got Cr2O7 2 minus goes to Cr3 plus. You know, it's funny, I just have a flashback to 1991. I worked at the Winnipeg Adult Education Center in the evening, and we talked about balancing equations. And we did one, and it took a real long time to do it, but we managed it. It took like a half an hour for one of them. And I said to myself, and then I said out loud, I wonder if I'll be doing this 30 years from now. And lo and behold, I am doing this 30 years from now. Groovy, man. How about that? 30 years. That was my flashback. Okay, so oxidation. Really, I just had that. I remember someone saying, yeah, you will be. Yeah, fine. Fe2 plus goes to Fe3 plus. So the ions are balanced, 1 and 1. I got a charge of 2 plus on the left and 3 plus on the right. So I want to balance for the charges because the masses are balanced for the same number of symbols. I don't have to worry about hydrogens or oxygens or anything like that. Oxidation, you must have an electron, at least one, on the right hand side. So now I put a little B in front of it. Bohr. Oh, Niels Bohr. No, it has nothing to do with Niels Bohr. This just means the balanced oxidation half reaction. The reduction half reaction, I'm going to put a 2 in front of the chromium, 3 plus, because the chromium symbols have to be balanced. Now I see the 7 oxygens. In acidic environment, and in basic environment, you have to balance the oxygens by putting in waters where appropriate. So I'm going to put 7 H2Os here. I can't put them on the left-hand side because then I'd have 14 oxygens on the left-hand side. So I put 7 H2Os on the right, and that's all special, so we're happy about that. But now we've introduced hydrogen, 14 of them, so I've got to put 14 H plus on the left-hand side. You don't put H's, you put H pluses. Okay, it's the acidic environment. But now reduction means gaining electrons, so I have to balance for charge. Electrons are being consumed, so they are on the reactant side. How many? Well, let's see. I got 14 positives and 2 negatives, so I got 12 positives on the left. I got 2 times 3, 6 positives on the right. So I've got to put in 6 electrons here, because then I'll have the same on both sides, 6 on both sides. Some students think that, oh, I have to have 0 as my net charge on the left and 0 as my net charge on the right. And that is not correct. You just have to have the same number on either side. So now I get the balanced reduction half reaction. Now I want to get the whole thing together, get the band together again. I can't just add the Bohr and the Bohr together because I can not have electrons left over when I combine them. Right now I got 1 electron on the right and 6 electrons on the left, so I have to take 6 times the Bohr. I'm finding the least common multiple of these, so I get 6 Fe2 plus goes to 6 Fe3 plus 6 electrons. And now I add these together, so the 6 electrons cancel out, and I end up with 14H plus Cr2O7 2 minus plus 6 Fe2 plus goes to 2 Cr3 plus 6 Fe3 plus 7 H2O. And then I look and see if it's balanced. I got 2 chromiums on the left, 2 chromiums on the right, 6 irons on the left, 6 irons on the right, 14 hydrogens on the left, 14 hydrogens on the right, 7 oxygens on the left, 7 oxygens on the right. Charges, 14 minus 2 is 12, plus 12 is 24, 2 times 3 is 6, plus 6 times 3 is 18, 24. Everyone's happy. Everyone's happy except the silly, well, I almost said the silly book, don't say that. Except the book, which doesn't like to keep it in H pluses. They want to have it in H3O pluses. So I'm going to add 14 H2O on the left, which means I have to add 14 H2O on the right. So 14 H2O plus 14 H plus gives me 14 H3O plus Cr2 O7 2 minus plus 6 Fe2 plus goes to 2 Cr3 plus 6 Fe3 plus, and then I got 7 waters, another 14 plus 21 H2O. And what does the answer say? 14 H3O plus Cr2 O7 2 minus plus 6 Fe2 plus goes to 2 Cr3 plus 21 H2O, and they left off the 6. Huh. They just left off the 6 Fe3 plus on either side. Imagine that. Okay, so let's try another one. Okay, oh, when I get it right, I like to give myself a little smiley face. Okay, oh, I'll make it a Martian for fun. Okay, let's go to, well, let me open, I know I'm going to be doing this again, so let's go to new. Okay, and I'm going to need all that space, right? So image resize. Oh no, I think I didn't want to do image resize. I want to do image canvas size. Actually, it doesn't make a difference at all, does it? So example 17.4, you can try the practice one. And example 17.5, is this one special at all? This is the one we did. 14. Oh, that was just a carryover, that's why. Okay, let's do one in the basic environment. Example 17.6. Oh, it's no, this one's going to be acidic environment. Okay, let's try this. Example 17.6. So I was saying it was a typo, but it just wanted you to balance the half reactions. Oh, really? It split it up so you would balance each half reaction first and then do it together. Come on, it's good to have a little bit of hand holding, but that's a little bit in excess, I think. Okay, anyways, my opinion, and I'm right. Okay, so let's go to the example 17. 6 on page 839. 17.6, page 839. So we're going to have H2SO4 plus C goes to form CO2 plus SO2. So that is not balanced. Do I know it's balanced? I know it's not balanced because I have 4. Well, because I have no hydrogens on the other side. You can't just put in H2 on this side because you aren't creating hydrogen gas on the right hand side. So let's assign the oxidation numbers. Oh, I'm not being color coded, am I? So hydrogens plus 1, oxygens minus 2, sulfur then has to be plus 6. Carbon is 0, oxygens minus 2, carbon's plus 4, oxygens minus 2, sulfur's plus 4. So the sulfur goes from plus 6 to plus 4, so that's reduction. The carbon goes from 0 to 4, so that's oxidation. The hydrogens and oxygens, they'll take care of themselves as we go through. So the oxidation half reaction is C goes to CO2. That's just the bare bones. We're going to do more. The reduction half reaction, H2SO4 goes to SO2. So the oxidation half reaction, we got C goes to CO2. So carbons are balanced. I got 2 oxygens there, so I got to put 2 H2Os on the left-hand side. but now I got to put in 4 hydrogen pluses on the right hand side, and I got to balance the electrons, so I'm going to put 4 electrons over here. So that is now balanced. Reduction half reaction, the sulfur is good. I got 4 oxygens on the left and just 2 here, so I got to put in 2 H2O. You'd get stuck if you said, oh, I'll put a 2 in front of here, but then your sulfur would change and you'd end up in this endless loop, this infinite loop of disaster. So you don't do that. You put in the H2Os, 2 of them. So that gives me 4 hydrogen symbols, but I only have 2 hydrogen symbols here. So I got to put another 2, and you put those as H pluses. So 2 H pluses. And electrons go on the left-hand side with reduction. The right-hand side is neutral. This is 2 plus, so this has to be 2 electrons. And that's now balanced. If you want, you can stop and double check that everything works out okay, that everything is awesome, as they say. Okay, 4, 4, 1, 1, 2, 2, those balance. Not a bad idea to do that. And now you want to combine them, find the least common multiple. For the electrons, you got 4 and 2, so the least common multiple is 4. So I got to multiply 2 times the Beher all the way through. So I get 4 electrons plus 4H plus 2 H2SO4 goes to 2 SO2 plus 4 H2O. And the Bohr was 2 H2O plus C. I'm just rewriting it so I can cancel things out better. CO2 plus 4H plus 4 electrons. Then we add them together. The 4 electrons cancel. Typically, you put the H2Os and the H pluses at the extremities in your equation, and whatever you're given, you try to keep that same order. So I'll have 2H. This is an interesting one, actually. Look at this. This happens sometimes. You pretended it was an acidic environment, but actually it doesn't care what the environment is because the 4H pluses cancel out. So that happens sometimes. And another thing that happens sometimes is you have H2Os on both sides. You have 2 on the left and 4 on the right. So your net is 2 on the right. Okay? So I end up with 2H2SO4 plus C goes to CO2 plus 2SO2 plus 2H2O. Let's check this. I do the non-hydrogens and oxygens first. So I got 2 sulfur, good. 1 carbon, good. Now the oxygens, 8, 2, 6, 8, that's good. And the hydrogens, I got 4 and 4. So that is good. So our final value is C plus 2H2SO4 goes to CO2 plus 2SO2 plus 2H2O. Okay, the practice exercise 17.6. In acidic environments, I'm going to let you try that one on your own. I'm going to look at one now involving basic solution. So this is example 17.7. This is Clorox bleach. And if you use ammonia at home, never mix it with the bleach because you get chlorine gas and ammonia. So here it is, and this is sometimes you hear people talk about this who are into cleaning. They just say, oh, I'm going to use this chemical and that chemical. Mix them together. Nothing bad will happen, will it? Yeah, things can go wrong. And if you're really interested in that, I think it's called bathtub bleach. But on my podcast, subscribe for free, All This Science, you will see a example of that. So, that actually was a guest podcaster from the United States who wanted to talk about her having to a hospital because she was scrubbing a bathtub with bleach and then she used ammonia after and got overcome with these noxious gases. And I said, sure, you can talk about that if you want. And that became the most popular podcast of all time. Okay, so, and if you believe that, so here we go, example 17.7. Now, it's a bit more complicated in the actual mixing process, what we have, but a simplification, you take ammonia, I mean, it's really ammonium hydroxide, but it's okay. This is page 840. example 17.7. So NH3 plus OCl minus goes to Cl2 plus N2H4. Okay, so you bleach, it is the hypochlorite ion that does the work. It helps to kill bacteria, uh, oxidize to change the color of stains. And so let's balance it, but this time we're balancing it in basic solution. So the trick is pretend it's acidic, and then at the very end put in OH minuses wherever there were H pluses. Okay, so let's decide what's oxidized and what's reduced. Let's change the color here. So, should we change the color for the number? Oh, that's fancy. Hydrogen is +1, nitrogen is -3. OCl minus, oxygen is -2, chlorine is +1, Cl2 0. Hydrazine, hydrogen is +1. And what the heck is the hydrogen? I guess it's going to be -2, right? It's -2 times 2 is -4, and +4 is 0. Okay, so the nitrogen goes from -3 to -2. So that, in fact, is a oxidation because it's getting less negative. And hydrogen stays the same. Oxygen, well, will stay the same. Chlorine goes from +1 to 0. So that is a reduction because the oxidation number is going down. Okay, so we have an oxidation half reaction and a reduction half reaction. How do I make it darker? Oh, look, there's different colors I can choose. Secondary colors. I don't even know what that means. Oxidation half reaction. NH3. I don't want that. I'm going back to primary, okay? I'm going to get it darker. There you go. Oh, hey, look at this. Black. Oh, didn't even see that. NH3 goes to, now we're talking, N2H4. Okay, and the reduction half reaction, OCl minus goes to Cl2. The pros leave space on either side of these to fit in electrons and waters and H pluses and OH minus and all that stuff. So you want to be a pro, right? So leave some space on both sides. Take it from someone who's been doing it for, well, I've been teaching balancing for 30 years, but I've been doing balancing since 1970, 79. Oh gosh, 1979. How many years is that? 89, 99, 2009, 2019. And I have no idea what the year is now. It's past 2021. So that is 40 something years, which some of you feel is the length of this particular lesson, right? So I got a 2 in front of there. So the nitrogens now are balanced. I got 6 hydrogens on the left. I got 4 hydrogens on the right. I don't use any H2Os. I just go straight to, because I don't have oxygens. So I can't breathe. I don't have oxygens. So I have 2 H pluses over there. Okay, stop that. And so now that's balanced. But now I have a charge of 2 plus on the right. And I have to look and say, have I done something wrong here? I was too busy telling jokes. NH3 and 2H4. And ha about it. Nitrogen -2. Chloride is reduced. I got 2 NH3 goes to N2H4. 6. I need 2 H pluses. But then I would need electrons on the right hand side, would I not? Okay. So here I am boasting about how many years I've done this for, and now I'm stuck. Is this one where I really do have to do the OH minus? let's look at the reduction half reaction. OCl minus goes to Cl2. I know I'm going to need electrons over here. Oh, I know I need electrons here. Oh no, I'm okay. I'm okay. I need 2 electrons on the right-hand side here, right? Oxidation has electrons on the right-hand side. Why was I going on the left-hand side? I don't know. Okay, maybe I'm doing this all on purpose to make sure you're awake. Okay, so I got, do you believe that? 6, 6, yes, now we're bounced to oxidation half reaction. The reduction half reaction, I got the oxygen, I got a chloride, I got 2 chlorides here. So let's bounce for the chloride first, right? So I gotta put a 2 here, and now I have 2 oxygens. So I gotta put in the H2O. How many? 2 of the H2Os. Now the Cl's are balanced, the O's are balanced. I got 4 hydrogens there, so I got to put 4 H plus. So I'll put it on the left hand side. Okay. And then I'm going to put in 4 electrons here. So that's a balanced reduction half reaction. So 2 oxygens, 4 hydrogens, 2 chlorines, 2 chlorines. And I'm now looking and I'm seeing something here, which is always good. Why you should check, because my right hand side is neutral. I'm 4 and 4 be 0, but there's still a 2 minus here, right? So I have to only put in 2 electrons, not 4 electrons, but just 2 electrons, right? Because I have a minus here, and that's a common mistake, and I just made it. But I fixed it. So 2 minus and 2 minus is 4 minus, so that's why I got 4H plus. Now I look and I say, oh, the electrons cancel out nicely, so I don't have to do any fancy manipulating. And I'm going to get 4H plus 2 NH3 plus 2 OCl minus goes to Cl2 plus N2H4 plus 2H2O. I got a 2H plus there. And I look and I say, oh, I had 4H plus on the left and 2H plus on the right, so I'm going to cross those out and just get 2H plus on the left. So if this was done in an acidic environment, this would be the answer. And you see why my method is way better than what they're talking about, because you can answer 2 things at once. Okay, is all my balancing good? All my balancing's good, and I have to go. Yeah, that's good. That looks good. But it didn't ask for acid environment. It asked for basic environment. So I'm gonna add OH minus to both sides. How many? 2. So if I have 2 OH minus here, and I'll put 2 OH minus there, then the 2 OH minus plus the 2H plus gives me 2H2O. So I get 2H2O plus 2 NH3 plus 2 OCl minus goes to Cl2 plus N2H4 plus 2H2O plus 2 OH minus. And my 2 H2Os actually cancel. So when all is said and done, my final answer is 2 NH3 plus 2 OCl minus goes to Cl2 plus N2H4 plus 2 OH minus. 2 nitrogens, 2 chlorine symbols, 2 chlorine symbols, 6 hydrogens, 2 O's, 2 O's, 2 minus, 2 minus. All is good. And let's check that answer. 2NH3 plus 2 OCl minus goes to N2H4 plus Cl2 plus 2 OH minus. Okay, let's try one more. Section exercises are more about balancing, and you can try those. But let's try practice exercise 17.7 in basic solution. Okay? So let's go File, New. Okay. Image, canvas size. $130. Okay, I don't know why it's going like that. File, new. I'm going to just keep the canvas size this way, fine. Okay, what do we have here? MnO4 minus plus CD. Oh, now it got bigger. Go figure. MnO4 minus plus CD goes to form MnO2 plus CD OH2. So practice exercise PEX 17.7. So you want to exercise your PEX. All right? My six-pack became a 2-liter to get over. Aha, funny jokes. Okay. Well, you try to make this interesting. Okay, here we go. Change here. So, MnO4 minus, oxygen minus 2, manganese plus 7, cadmium all by its lonesome 0. Right hand side, oxygen is minus 2, manganese plus 4. Cadmium hydroxide. Cadmium has to be plus 2 because the hydroxide is minus 1 and there's 2 of them. Oxygen is minus 2, hydrogen is plus 1. So the manganese goes from 7 to 4, so that is a reduction. And the cadmium goes from 0 to plus 2, so that's an oxidation. So the oxidation half reaction is cadmium. This is just the bare bones. We're going to fill it in. Cadmium goes to cadmium hydroxide. The reduction half reaction, MnO4 minus, goes to MnO2. Okay, oxidation. We got cadmium, we got cadmium. We got 2 oxygens and we got 2 hydrogens. Do the oxygens first. So I'm going to put 2H2O here. I know I'm going to have electrons on the right hand side there. I'm going to put 2H plus on the right and 2 electrons, 2H plus. I'm pretending it's acidic and then I'll make it basic. Because that means 4 hydrogen symbols, 2 and 2 is 4, 2 oxygens, cadmium, cadmium. That's all balanced. So that is the balanced oxidation half reaction. The reduction half reaction, the manganese is good. I got 4 oxygens, so I'm going to have 2 H2O here. Okay. And now the oxygens are good. I got 4 hydrogens, so I've got to put 4H plus MnO4 minus. So that's 3 positive. So I need 3 electrons. So that's the brr. So 3 electrons, and now there's 4 electrons, 4 negatives, and 4 positives. Okay. Now this is a good one because this is the first one we've seen where we're going to have to manipulate both equations because the least common multiple of 2 and 3 is 6. So we're going to have to take 3 times the Bohr and 2 times the brr. Okay, so 3 times the Bohr, so that's 6H2O plus 3CD goes to 3CdOH2 plus 6H plus 6 electrons. And 2 times the Bohr, 6 electrons plus 8H plus 2 MnO4 minus goes to 2 MnO2 plus 4 H2O. We're going to add these together. So the 6 electrons cancel. I got 6 H2O on the left, 4 on the right. So my net is 2 H2O on the left. I got an 8H plus on the left and a 6H plus on the right. So my net is 2H plus on the right. So I'm trying to do some of that housekeeping before I now add them all together here. So I'm going to get 2H plus 2H2O plus 2 MnO4 minus plus 3CD goes to form 2 MnO2 plus 3 CD OH2. I think that's it. Let's see. Let's look at charge first. Charge looks good. Now look at symbols. 2 manganese, 3 cadmiums, 3 cadmiums. 2 and 8 is 10 oxygens. 4 and 6 is 10 oxygens. 6 of each on those sides. So if this was in acidic environment, this would be the case. I mean, I could add H2Os on both sides and have it all in terms of the H3O plus, but it's in basic environment, so I can skip that step. But what I do want to do is add 2 OH minuses to both sides. So if I add 2 OH minuses here, that becomes 2 H2Os. And I add 2 OH minuses here. Okay, 2 H2O and 2 H2O gives me 4 H2O. So you end up, and I don't even have to look at the back of the book. I'll know if it's right or not, because if it's not right, it won't balance. Cadmiums are good. Manganese are good. Oxygen's 4 and 8 is 12. 4 and 10, 12, that's good. Hydrogen's 8. And here I got 6 and 2 is 8. Charge 2 minus, 2 minus. We got it. Good work. How about that? Okay. So now we balance this. We talked about the redox one with the ammonia and bleach. Galvanic cells, section 17.3, and we're going to hold off on that to our next lecture. Okay, so that'll be the start, WU17 lecture 2. Above what we just finished is WU17 lecture 1. Okay, so try some of those balancing ones, end of chapter questions, whichever ones you want. You'll know if you're right or not, and I have a feeling you're going to do just fine.